Remember valence bond theory? Do you remember hearing about valence bond theory? Okay, that's okay. So we can describe the bonding in complex ions using valence bond theory. Valence bond theory describes chemical bonds as the overlap of orbitals. Typically we see one half-filled orbital on one atom and a half-filled orbital on another atom, and they overlap. In a coordinate covalent bond, you have a completely full orbital with 2 electrons overlapping with a completely empty atomic orbital. In these complex ions, the empty orbital is on the metal. And so the ligand always has a lone pair, and it's that lone pair is in an orbital. That orbital overlaps with an empty orbital on the metal ion. So the orbitals on the metal ion are hybridized according to the geometry of the complex ion. So if you need a refresher on valence bond theory, see me later. We don't have time to go over that again. So if we have a linear geometry, then we have an sp hybridization. Tetrahedral has 4 groups, so we have 4 orbitals hybridized, s, p, 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 s, p, p, p. There, 4 sp3. And square planar, I don't know why they put the D first. Well, the D is from a lower primary energy level. In Chem 1A, we called it sp2. sp3. What? Sorry. Brain fart. Okay, so that one's weird. SPD. D, sp2. Okay, so that's a little different. And then octahedral, D2, sp3. Yeah. We won't worry about it. So valence bond theory explains the geometry, but it doesn't explain other things that we observe in complex ions, such as color and magnetism. Complex ions often have are colored, sometimes very beautiful colors, and so we need something called crystal field theory to explain colors and magnetism. So these complex ions form because we have attractions between the electrons on the ligands and the positive charge on the metal ion. But the ligand electrons also repel the metal's electrons that are in unhybridized d orbitals. So the octahedral ligands overlap with 2 d orbitals, and that increases their energies more than the 3 d orbitals that are in between the ligands. And that probably made 0 sense, so hopefully this picture will help. So here we have, in this octahedral shape, we have the ligand overlapping with orbital lobes. So we get this a strong repulsion here with these 2 d orbitals. Remember the shapes of the d orbitals? They're double lobed and they're arranged like this, and then there's that one weird one, right? So here, for these 2 d orbitals, the ligands match up with the lobes, and so there's repulsion there. For the other 3, the ligands fall between the lobes of those d orbitals, and so the repulsion here is weaker. So the energy levels of the d orbitals on the free atom get split. 3 of them are only slightly higher in energy because of weak repulsions, and 2 of them are significantly higher in energy because of the strong repulsions from the geometry. This difference in energy is the crystal field. Any questions? Did that make any sense? Do you see how we're looking at this octahedron and we're seeing how the ligands here overlap with the unhybridized d orbitals? And you see that three of them, they kind of fit in here nicely, and these three are just getting in the space of the d orbitals. And so these are not happy, and these are okay. So these are unhappy is high energy, and okay is just a little bit higher energy. So the crystal field splitting energy, that difference, it's the difference in energy between the split d orbitals. How much that splits depends on the ligand and the metal. So we divide these into strong field complexes with a large splitting energy and weak field complexes with a small splitting energy. And this orbital splitting leads to the beautiful colors of many of the complex ions. So color, if you remember, is related to absorption of light energy by electrons in molecules. If you have something that appears black, like the inside of my iPad case appears black, it's because it's absorbing all the wavelengths and not really reflecting anything. If you have something that appears white, like my Apple Pencil, it's transmitting or reflecting all of the wavelengths. And if you have something that's a color, it's absorbing some of the visible light and transmitting other parts of the visible light. So this red solution is not absorbing the red light. The blue solution not absorbing blue. So it transmits the color that it appears, or it transmits most of the light but absorbs the complementary color. So this gets all into color theory. So this molecule, this complex ion is purple because it absorbs strongly in the yellow-green region. If we look at the absorbance as a function of the wavelength, we see that as you increase the wavelength, it absorbs more and more, and so very strongly in this yellow-green region, and then it falls off. So you're taking this part of the color out, and you're seeing what's left. And so you're seeing purple. It's a combination of this and some of this red stuff up here. Okay? So spectroscopy, and this is what we're going to be doing in lab today, spectroscopy, we can measure the wavelength absorbed when an electron makes a transition from lower energy d orbitals to higher energy d orbitals. And so here we can see that this absorbs pretty strongly, just above 500 nanometers. So we can calculate the crystal field splitting energy by looking at the energy of the photon, which is related to its wavelength, right? So the energy of the photon is Planck's constant times the frequency, or Planck's constant times the speed of light divided by the wavelength. We can measure the wavelength here, and so we can calculate the splitting energy. So the complex ion, should we go for it? Pentaamine nitro cobalt 3, I think. The NO2 is a -1 charge. Yeah, is yellow.
Oh, okay, yeah.
Estimate the crystal field splitting energy in kilojoules per mole for this ion. Blah. Okay, so the complex ion is yellow. So we could look at this color wheel. If it's yellow, and we don't have any information like this, it's yellow, then we can say, well, it's probably absorbing strongly on the opposite side here. So 430, 400, call it 415. So we'll say that lambda is 415. We don't want the color that is observed because that's not absorbed. We want the color that's absorbed. So our lambda for this equation is going to be 415 nanometers. So lambda equals 415 nanometers. The energy of a photon is equal to hc over lambda. So we can calculate the energy of one photon. Oh, Planck's constant. 6.63 times 10 to the minus, I don't remember. 34, yeah, 34 sounds right. That's what books are for. Planck's constant, yeah, 6.63 times 10 to the minus 34. And the units on that are joule seconds. Speed of light is, let's go with 3 times 10 to the 8th, yeah. I learned it in centimeters at some point, and that's why I tend to put the 10 in there. And that's meters per second. And then we're dividing by the wavelength. What unit would be good for the wavelength? Meters. Meters would be good. So instead of doing nanometers, I'm going to do 415 times 10 to the minus 9 meters, because this is what nano means. Okay? So 6.63 times 10 to the minus 34 times 3 times 10 to the 8th divided by 415 times 10 to the minus 9. And that gets us 4.79 times 10 to the minus 19. And the unit that's left there is joules. Is that the answer? We're supposed to have it in kilojoules per mole. This is the energy of one photon. How many photons in a mole of photons? Avogadro's number.
I know that now.
So we could take this, let's put it down lower, 4.79 times 10 to the minus 19. Let's call that joules per photon, times 6.022 times 10 to the 23 photons per mole of photons. And then we want this in kilojoules, so kilojoule 1 times 10 to the third joules. (287 kilojoules per mole). Is that an exact calculation? No, it's not. It's an approximate calculation. Any questions? Yes. How did I get the 415 nanometers? So we're told that the complex ion is yellow. That means it's not absorbing yellow. So in the absence of any information, like an absorbance graph like that, what we can say is, well, if we're seeing yellow, it must be absorbing over here somewhere. And so let's just put the middle of the opposite of the middle of yellow. Yeah. Any other questions? So the ligands affect the magnitude of the crystal field splitting. So what's called the spectrochemical series. lists ligands in order of their ability to split d orbitals. So cyanide splits them a lot, and we go through this list, and iodide splits them the least. So if you have iodide as your ligands, typically you're going to have a weak field, crystal field, and up here it's going to be strong field. The metal ion also has an effect. The higher the charge, the closer the ligands get pulled in, and then you get more repulsion, so a larger crystal field splitting. So magnetic properties, Hund's rule says that electrons occupy degenerate orbitals singly when possible before they pair up. So when those d orbitals get split, the lower energy orbitals are going to fill first. And when those are half filled, the next electron can either pair with an electron in one of those half-filled lower energy orbitals, or it can go into an empty orbital that's higher in energy. And what it chooses will depend on how large the splitting is. So here, if we have the splitting, the difference in energy between the higher energy and the lower energy d orbitals, this is large, and here it's small. So we have 6 electrons to stick in here. We're going to go 1, 2, 3, and this next one says, well, I could occupy this orbital with another electron, or I could pay a large amount of energy to go up there. I'm cheap, I'm going to stay down here. And so they'll fill these up. When this gap is small, we go 1, 2, 3, and the next one says, I'm going to spring for my own orbital. It's just a little bit of energy. And then the next one says, I'm going to take this orbital, I'm going to have my own orbital. And then the 6th one has to pair up with somebody, so it's going to pair up with one of the lower energy ones. So this causes a difference in whether we have all paired electrons or some unpaired electrons. So this compound is diamagnetic, and this compound is paramagnetic. These half-filled orbitals, these unpaired electrons, will be attracted to a magnetic field. When we have all paired up electrons, they're slightly repelled by a magnetic field. So this is called diamagnetic, and I get those backwards, diamagnetic and paramagnetic. And what finally works for me is I think diamagnetic, di means 2, right? And in Noah's Ark, all the animals went in 2 by 2. And so here we've got 2 by 2 by 2, like Noah's Ark, right? Diamagnetic. Paramagnetic is the other one. Because the problem is, pair sounds like pair, right? P-A-R sounds like P-A-I-R, but it's not. Okay, it's not that. But di is always 2. So large splitting, large difference in energy, then we're more likely to have these electrons pair up. A small difference in energy, and we're more likely to have electrons go up here, more likely to have unpaired electrons. Does that make sense? So when you have complexes with strong field ligands, that difference in energy, the crystal field splitting energy, is going to be large, and so you're going to have fewer unpaired electrons, and so those are called low spin complexes. And with weak field ligands, where the difference in energy is smaller and the electrons are more willing to go up into the higher energy orbitals, we're going to have the same number of unpaired electrons as in a free metal ion. Those are called high spin complexes. Not all metal ions have an option or possibility of both kinds occurring. You have to have enough electrons that one of them would go up into the next orbital. So you have to have at least 4 electrons in your d orbitals. So we should be able to answer questions like this. How many unpaired electrons are there in the complex ion hexachloro? I don't know. It's a negative ion, and so then I think it becomes ferrate. Yeah, ferrate 3. Yeah, sorry. So what we have to ask ourselves is chloride a high field or a low field? And go back to this list, right? Weak field. Sorry, low field. Weak field. So chlorine's a weak field, so we're looking at a small difference in energy. So we could draw those orbitals, and this here, delta, is small. So the iron here is iron 3+, right? So then we have to look at how many electrons does iron 3+ have in the d orbitals. So iron, if we go across there, it's 1, 2, 3, I can't count, 6? It would normally be 4s2, 3d6. That's for an iron atom. But we've removed 3 electrons, so we got rid of those electrons, and we dropped this down to a 5. So we have 5 electrons to stick in there. Small field difference, 1, 2, 3. Where's the 4th one going to go? It's going to go up. 4, and the next one's going to be up there too, 5. So how many unpaired electrons? 5. Hexacyanocobaltate 6? No, 2. Cobaltate 2. The cyanide ions, -1. Overall -4 charge, so the cobalt must be cobalt 2+. So if we find cobalt, cobalt has 1 more proton and electron than iron, so it would be 4s2, 3d7. And to get rid of the 2 electrons, we're going to ditch those s electrons first. So we've got 7 electrons here. Then we have to ask ourselves, cyanide, strong field or weak field ligand? It's a strong field ligand. So here, this difference is large. So when we put our 7 electrons in here, 1, 2, 3, the next one says, I don't want to pay that big energy difference. 4, 5, 6. The 7th one has no choice, has to go up there. How many unpaired electrons? 1. Any questions? It always looks easy when I do it. Because I kind of know what I'm doing. So that was for octahedral. For tetrahedral and square planar complexes, the splitting pattern is different. For tetrahedral, it's the opposite of octahedral. If you imagine the different d orbitals in there, now these are going to fit between 2 of them and conflict with 3 of them. And so we have 2 orbitals that are lower in energy and 3 that are higher in energy. So the splitting's opposite. So these are usually going to be high spin, meaning more unpaired electrons than in the regular metal ion. And the difference, the crystal field splitting energy is generally smaller than for octahedral complexes. In square planar, it gets even more complicated. You end up with two that are lower, and then these three are different. Isn't that lovely? This occurs in D8 metal ions, and these are almost always low spin. Again, the same number of unpaired electrons as the metal ion by itself. So as you can imagine, there's a whole field of chemistry looking at these, right? Because there's all kinds of things you can investigate.